Okay, let me share my screen. So we will continue on sensor and transducer for subtopic temperature sensor. And then we have photodiode and phototransistor. Okay, before that, any question on chapter sensor? This is application of resistive transducers to engage. So I just review this chapter. So we have tools to engage. If the string gauge has two, if the bridge circuit has two strain gauge, these two strain gauges have the same resistance value, and R1 is equal to R3. And this is the example of capacitive transducer, variable plate transducer, where we have fixed plate and moving plate, and the application widely used in analog radio, where we tune this shaft to get frequency, or we also call it S station. We want to find the frequency of the radio. Okay, inductive transducer can be categorized into self-generating and passive. Okay, for self-generating, meaning that voltage is generated due to the relative motion between conductor and a magnetic field. For example, tachometer, which directly converts speed or velocity into an electrical signal, but the fundamental is induction. Okay. The relative motion induced so this is speed to be measured. This is shaft. Speed to be measured because tachometer converts speed into electrical signal. Okay, so we have permanent magnet here, north and south. Okay, this is brushes, commutator. We have resistance, and this is the meter, moving coil voltmeter. So when we turn this shaft, the relative motion induce the EMF in the coil. The EMF is directly proportional to the speed of the shaft. The commutator converts the angular velocity into an electrical voltage. Commutator converts the alternating current of the armature coil to the DC with the help of the brushes. The moving coil voltmeter measures the induced EMF. The polarity of the induced voltage determines the direction of motion of the shaft. The resistance is connected in series with the voltmeter for controlling the heavy current of the armature, this resistance. This is good knowledge. This is about DC and AC tachometer. DC tachometer generator uses the commutator and brushes, which have many disadvantages. Okay, these brushes and commutator have many disadvantages and require the periodic maintenance. AC tachometer has stationary armature and rotating magnetic field. Okay. No commutator and brushes. Thus, AC tachometer solve the problem. AC use full wave rectifier circuit here. Okay. What else? Okay, so now we go to temperature transducer. Temperature transducer, temperature is one of the most widely measured and controlled variable in industry. Okay, so there are two types of temperature transducer: passive and active. Passive transducer resistance change with temperature, so they need an electrical supply to give a voltage output. Why for active transducer? It is principle of generation of thermoelectricity generates an electrical signal directly in response to the physical parameter. Example for passive transducer is RTD and thermistor, and thermocouple is the example of active transducer. These are the differences between RTD, thermocouple, and thermistor. Okay, temperature range for thermocouple is the wide the range for thermocouple is widest compared to RTD and thermistor. Okay, the cost is moderate for RTD. System cost is highest for thermocouple. The best stability is for RTD. The best sensitivity is for thermistor. The best linearity is by RTD, and RTD is specified for general purpose sensing, highest accuracy and temperature averaging, thermocouple highest temperatures, thermistor best sensitivity, narrow ranges, point sensing. Okay, this is the relationship between the output of each sensor with temperature. Okay, so the output is in resistance, right? Okay, the output is resistance. So for RTD, the resistance is directly proportional to the temperature. Okay, thermistor, the output or the resistance is inversely proportional to the temperature. Okay, so this is RTD. So thermocouple, thermistor. Okay. RTD is resistance temperature detector. It's a temperature sensor that produces a change in resistance in a metal as a function of temperature. So, by measuring the resistance of the metal, its temperature can be determined. Okay. RTD commonly use platinum, nickel or copper wire whose resistance varies with temperature. Okay, so these are the example of RTD material: copper, nickel, platinum, tungsten. The temperature range in Celsius and the resistance coefficient. Usually use copper, so copper is widely used, but the best is platinum due to lower resistivity. Used as process temperature monitors because of their accuracy and linearity. Okay, so among these four material, platinum has the lowest resistance coefficient. Okay, so meaning that it is the best, okay, among this. Most RTD instruments use a Wheatstone bridge or its modified version as shown in figure below. So we have learned about Wheatstone bridge. Wheatstone bridge measure resistance. Okay, so it they have 4 arms here. Okay, to detect the small variations in resistance of the RTD. Okay, a temperature transmitter in the form of a Wheatstone bridge is generally used. So this is Wheatstone bridge. Okay, why we use bridge? To detect a small variation. So when there is small variation in resistance, we know that in Wheatstone bridge, when there is a small change in resistance in the arm, so it will give reading to the meter, right? Okay. The circuit compares the RTD value with the 3 known and highly accurate resistors. As the RTD temperature increases, the voltage read by the voltmeter increase. Okay, so at normal condition, meaning that no increase in RTD temperature, so the reading for the voltmeter is equal to, the reading is equal to class at the beginning, the reading is equal to the reading is equal to Saim Akil at the beginning, the reading is equal to, the reading of the voltmeter is equal to
0.
Okay. So when the temperature increase, the voltage read by the voltmeter is also increased. This is temperature transducer thermistor. Okay. So the graph for thermistor is opposite with the graph for RTD. Okay, so semiconductor material that exhibit a large change in resistor with a change in their body temperature. The word thermistor is a contraction of the words thermal and resistor. Type of resistor, negative temperature coefficient NTC and positive coefficient, positive temperature coefficient PTC of resistance. So NTC, decreasing electrical resistance will increase in environmental temperature. So NTC, okay, NTC is negative temperature coefficient. So meaning that when the temperature is increase, the resistance decrease. Okay, PTC, increasing resistor with increasing of temperature. Okay. Okay, class. You can read the rest of the chapter by yourself. Now, I want to discuss the solution for midterm test. Okay. So, where is the question? Okay, so this is the question of your midterm test. Inshallah, I will return your midterm test by this week. Okay, question number 1, referring to figure 1. Okay, this figure, the voltage reading. So, question number 1 is very simple question. Okay, as compared to question number 2, right? Question number 1, very simple question, but actually there is a mistake. Okay, the voltage reading at R2 10K was measured using a voltmeter having a sensitivity of 20 kilo ohm per volt. Calculate the voltage reading V2. Okay, it is the voltage across R2 and the percentage of error for each reading obtained with the voltmeter in the following range, 5 volt and 10 volts. Okay. So what is the key of the question? Find the VR2 and the error, percentage of error of the measurement. Okay, but I have two ranges of voltmeter, 5 and 10 volts. Okay, so how to find the VR2? Very easy, by using voltage divider principle only. Okay, so VR2 is equal to 10K divided with 40 plus 10K multiplied with the voltage source 50, we get 10 volt. Okay, very straightforward. Okay, and then how to find the percentage of error? So, okay, so now this is the actual reading. Okay, not the voltage reading by the voltmeter. So now we have to find the V measured by the voltmeter. Okay, but how to find the voltage read by the voltmeter? We should consider the resistance inside the voltmeter, right? Okay, so how to find the resistance inside the voltmeter? We use this formula, R is equal to SB range, right? R of the meter is equal to S sensitivity of the meter multiplied with V range of the voltmeter. Okay, so we have the information of sensitivity 20K. Okay, multiply with the voltage range. Okay, number one is 5, so the voltage range is 10K. Actually, this is the mistake where the actual reading is 10 volt, but the voltage range for the first voltmeter is 5 volt. Okay, so the range of the voltmeter should be larger than 10 volt. So this is a mistake. Mistake here, mistake of the question. Okay. But never mind. I will consider maybe we have a few versions of the solution. Okay, I will consider this mistake. Okay, so if you ignore the range of this 5 volts, so the flow of calculation is like this. So after you calculate the R of the meter, so now we can calculate for the R equivalent at this portion, right? So R of the meter, make it parallel with the R2, 100K just now. 100K is parallel with 10K, we get 9.091 kilo ohm. So after we put the voltmeter parallel to R2, so the equivalent resistance here is changed. Okay, it will decrease the resistance here, equivalent resistance here, because of the voltmeter loading effect. Okay, so it will decrease the R equivalent. So now we calculate for the V measured across R2. We take the new R equivalent, okay, divided with this summation of 40 and 9.09 multiply with the voltage source, we get 9.26. This is the measured voltage across R2 by using the first voltmeter range. Okay, and we can calculate for percentage of error. Any question up to here? Can I understand? Azim boleh? Boleh? Understand or not?
Yes.
Okay. Okay, now the same goes for the second voltmeter. We just change the range of the second voltmeter 10. So this is the new R, the R of the meter 200K, and then we calculate for the R equivalent. So far 9.524 kilo ohm. It is lower than R2 because of voltmeter loading effect. Okay. And then we can calculate for the voltage measured by the voltmeter. Okay, we use the voltage range of 50. Okay. 50, and then we can calculate for the error. So this is the error for voltmeter number 2. This is the error for voltmeter number 1. The next question is give your comment on the voltage readings and measurement produced in question here, and okay, this give a suggestion on how to reduce the loading effect on voltmeter. Okay, so I can accept any answer that is suitable. Okay, so this is, so you can answer like this. The 10 volt range introduce lower error due to higher loading, okay, caused by higher V range. Okay, 10 volt higher V range than 5 volt, it produce higher R of the meter, right? Higher. Okay, 200 K is higher than 100 K. So it gave lower error. Okay, 3.8 as compared to 7.41%. Okay, this contribute to marks. Okay, suggestion: the multiplier resistance used for the voltmeter can be as high as possible to reduce the current that passes through the PMMC meter. Okay, multiplier resistance meaning that this out of the meter 200K, 100K. Okay, actually this might include internal resistance of the meter resistance. Okay, meter resistance instead of multiplier resistance. So we can use the as high as possible. Okay, multiplier resistance RS. Okay, as high as possible. So actually the R here that we have calculated is actually combination of RS and internal resistance of the PMMC. Okay. Okay, and then the other suggestion is by increasing the sensitivity of the voltmeter. So use higher sensitivity of the voltmeter. Any other answer, if it is acceptable, so I will give the mark. Okay, any question before we go to C? No question. Okay, so C, as an instrument engineer, you are required to design an ohmmeter. Okay, therefore specify at least 3 scales to be marked on the meter face. Sketch the meter face by marking the scales. The specified specs are indicated as in table 1 below. So we are given current, RVSD, meter resistance of meter movement, and the battery. So the question is to find 3 scales to be marked and then sketch. Okay, that's all. So what is the step to find the scale? What is the first step? Okay, the first step is to find the RS, or RS is series resistance, or we can call it as multiplier resistance. Okay, so RS is equal to, okay, so I'm sure that you know how to calculate this. So R is equal to V over R. Okay, V over R. R is equal to V over R. So RS, okay, we have a series circuit where RS is in series with RM and RX, right? Okay, so RS is equal to V over I, and then minus RM and RX, right? Okay, so to find RS, we will short circuit the probes of the ohmmeter. So RS will become 0. Okay, so actually 3 divided by 1 milli minus 100. 100 is RM, and minus 0. Actually 0 is RX. Okay. the resistance to be measured. It is equal to 0 because of short circuit the probes. So 3 divided with 1 milli minus 100 ohm, and we get the RS. Okay, so now let's try for 20. So up to you, you can use any deflection. Let's say 20% deflection, so 3 divided with, so now the current will become only 20% of the full scale. So 0.2 multiplied with 1 milliamps. Minus 2.9K minus RM 100, you get this. So at 20% deflection, the RX is 12K. Okay, same goes for other deflection. Let's say you try 50%, 3 divided with half of the current, okay? Half of the current, and then minus the RS minus RM, we get this. And then let's say you try for 75% of the deflection, so it will become this. Okay, the next is to sketch. Okay, so just sketch, and then 0 must be at the right side. And then this is about 20%, so we get 12K, right? So this is 12. Okay, 12K. Betul kak kira ni? Okay. Class, try to calculate. Well, okay. 12K, and then this one is okay. So you will get 3 marks for the sketch. Okay. Any question for question number 1? No question. So we go to question number 2. Is there any question? No question. Okay, this is question number 2. Figure 2 shows the multi-range AC voltmeter. So this is AC voltmeter multi-range. Given the voltage range V3 to 1 are 10. Okay, so when we tap this point, okay, selector to V3. Okay, so the V3 is 10V RMS. Here at V2, 50V, and at V1, it is 100V RMS. Okay. respectively. The PMC spec full scale differential current 100 microamps and RM is 10 kilo ohm. Calculate RS1, RS2, and RS3. Okay, series resistance for 1, 2, and 3. Okay, so now okay. So this is method 1 where we convert the AC voltage, okay, the AC voltage of each voltage range to DC. Okay, we convert it to DC, meaning that we average. Okay, and then we calculate the rest calculation in DC. Okay, DC. Okay, but or you can calculate as in your notes. Okay, so let's start with RS3. Okay, now we type this selector to V3. Okay, meaning that current will flow through RS3 and RM. Okay, so how to find the RS3? Okay, how to find the RS3? RS3. So this is the formula. This is the typical formula, the general formula for RS. RS is equal to R total minus RM. Okay, because in this circuit, when we type the selector at V3, we will only have two resistors, RS3 and RM. Okay, so RT, we know that RT is equal to SV range. Okay, so now I remain the calculation in AC. Okay, so this solution, okay, the provided solution here use DC calculation. Okay, so you need to convert the AC voltage here to DC. Okay, so this is halfway of full rectification, halfway of full wave rectifier.
Half.
Why half?
Half.
Diode ada satu.
Yeah, because we have only one diode here, so this is half wave rectifier. So that's why this calculation convert, okay, to DC calculation or to average by multiplying 0.45, by multiplying the AC range V range with 0.45. If this is full rectifier, so we multiply the RMS voltage with Ramona.
Yeah.
If this is full rectifier, so we multiply the RMS voltage with
0. Full ke?
full.
Full
Let's say full.
0.9.
Yes, good. We multiply with 0.9. So instead you can use AC calculation. Okay, this is DC in DC calculation. You can also use AC calculation. Okay, as in your notes. Okay, so we should use SAC and VAC. Okay, so SAC is equal to 0.45 SDC. Okay, SAC is equal to 0.45 SDC. This is fixed, okay, as we have learned before. So, and then VAC range is as mentioned in the equation. And then minus RM is provided in equation 10K. So, we have to find SBC. SBC is equal to 1 over IFSD. Okay, so you just calculate this. IFSD is equal to 100 micro and you will get 35K. So RS3 here is 35K. Any question? It is same as in your notes. Okay. So this question is created by Dr. Zulkifli. So the solution here is provided by him. So this is converting ADC to AC. So each step will be given marks. Okay, but when you use AC calculation, so you will only have this step. Okay, and then the same goes for the range. Okay, but you must be very careful when we type the selector to V2 here. We will have, okay, what are the resistors involved in this circuit when we type the selector at V2? What are the resistors involved in the circuit? When we type the selector at V3, we have only three resistors, which are RS3 and RM. Now we type the selector at V2. What are the resistors involved in the circuit? Akmal Lukman.
Yeah.
Now we type the selector at V2. What are the resistors are in the circuit? Involved in the circuit now. Cepat jawab. Nanti masa. Akmal Lukman.
Tak pasti tu.
Can you answer this question well?
Tak pasti tu.
Okay, Ahzad. Please answer. Do you have class at 4 p.m?
No.
Anyone
Yes,
have
okay.
class? Ada kan?
I got class okay.
Yeah. Okay. So now we type the, okay, if you have class at 4 p.m, you can just leave my class if you want, okay, at 4 p.m. Okay, now we type the selector at V2. What are the resistors involved in the circuit now? MT.
Ya saya.
Jawab.
Apa dia tadi resistor yang involve
Ya, 2 kali ulang soalan.
dekat wattmeter 1, R1, R2, R3.
I cakap the selector now is at V2.
Dekat V2, R2 dengan R3.
Okay, good. So we have R2, R3, and satu lagi we have RM, okay? So this is the calculation for MT. Tutup suara.
Saya dah tutup.
Okay. So now we calculate for RS2. Okay. We want to calculate for RS2. So meaning that RT minus RM and RS3. Okay. So the calculation is the same. We repeat the same. We change V range into 50. Okay. Now V2 is 50. But we have to subtract with RM and RS3. We have calculated RS3. It is 35 kilo ohm, right? That we have calculated before. Okay, and we will get 180 kilo ohm. Okay, so just now we have RS3 is equal to 35. Now RS2 is equal to 180 kilo ohm. Okay, now we type the selector at V1 and we will have all resistors in the circuit now. So that's why we want to find RS1. So equal to RT minus RM minus RS3 minus RS2. Okay, please put the value for RM, RS3, RS2, and we will get RS1. Okay. Any question for A? Okay, no question. So now we go to B. Maybe the most challenging question in midterm test. Okay, figure 3 shows the AC voltmeter that is given. So this is AC voltmeter. It is given to you to make a measurement of T240 VRMS from the TMB AC supply. However, the voltage range is lower than the voltage of the TMB AC supply. Okay, why? Because this range is only 40, right? The highest is 40. So the range for this meter is 40, but we want to measure for 240 VRMS. by using given AC voltmeters, but you must use this AC voltmeter, but you have to design the new AC voltmeter circuit. Okay, so you have to modify the construction of this voltmeter to measure the required voltage. Given SAC is voltmeter is 5 kilo per volt, assume the meter indicator will deflect 50% of full scale during measurement. So meaning, imagine that after you design the new AC voltmeter, and then you measure that this 240 VRMS, it will deflect only for 50%, meaning that it will deflect at the middle, right? It will deflect 50% of the full scale. Okay, so how? So now this is the old voltmeter here. Okay, Rs of this voltmeter is equal to SV minus Rm, right? So S is given 5K multiplied with the RMS of this, it is 40, and then minus Rm of this, it is neglected, right? Neglected. Okay, so Rs of this meter is 200 kilo ohm. Now, okay, this is the new voltmeter. This is the old voltmeter. Okay, where the VRMS of this voltmeter is 40. Okay, the V range of this voltmeter is 40. This is voltmeter, okay, voltmeter. This is the circuit for voltmeter. The voltage range is 40. The Rs is calculated 200K. The sensitivity. Now we design the new voltmeter, which can read for 240 VRMS, but the deflection is 50%. This is the new RS, okay? And then how to calculate? So 50% of full scale deflection, meaning that the full deflection of the meter will be 4AO VRMS, right? Am I right? Okay, the full deflection of the new voltmeter is actually 4AO VRMS, but when we measure the signal here, it will deflect at 50%. So meaning that the full scale is 4AO VRMS. Okay, so now RS new is equal to SB range minus R the old RS, okay? RS new plus RS old is equal to SB range. So 5K multiplied with the new V range, and then minus the old RS. So we get the new RS 2.2 mega. This is RS, the new. Okay, any question? Any question, class? No question. No question? You want to type something? No. If there is no question, then we can end our session. So I will upload this solution in MS Team. Okay, I will upload this in MS Team. Solution for Q1 and Q2. And then I will re-upload notes for chapter 7. Okay?
Doktor, maka midterm tak tahu apa-apa.
Belum lagi, nanti by this week insyaAllah I will key in SMP, or I will blast to WhatsApp group or MS Team. By this week I will return your midterm test. Okay, insyaAllah.
Doktor, apa chapter ni masuk final?
Chapter masuk final, all chapters will be covered in your final exam.
Ya. Chapter ni masuk ke?
Of course, not all chapters.
Oh,
All chapters will be covered in your final exam. This Friday I will I will let you know the structure of an exam. Okay.